Okay, good afternoon everyone, welcome back. Today I had promised last week we would be going over stack smashing in this lecture, but I had forgotten that we have a project review lecture today and stack smashing is going to be on Wednesday. Plus stack smashing is not going to be tested on the final, that's bonus content, so I figured we should spend today going over the project and other examples I prepared as well. Before getting into that, there's the homework, and before getting into that, I want to ask you all, maybe beg somewhat for you all to please complete the SPI ratings for me. So the SPI, Student Perception of Instruction, it's available now. My goal after graduating is to work in a primarily undergraduate institution where my chief responsibilities will be teaching. So in order for me to continue doing that, continue teaching and growing as an educator, hopefully, I would really ask for you all please to complete those SPI ratings. Strong ratings are good, but if you don't like me, if you don't like the way I teach, you don't like the course, you can mark all that down as well, of course. And I'll make an announcement about this, but I am allowed to do this by university policy if a majority of the class completes the SPI. So I'll say 70%. If 70% of the class completes the SPI ratings, I can give 1 point of extra credit to everyone. And I am allowed to do that. So please complete the SPI ratings.
What's the maximum points they allow you?
They don't say, but I bet they wouldn't. I don't know. That's a good question. That's a good question. Yeah. I need to find the exact page that says I'm allowed to do this because I need to be able to cover myself in case anybody questions me. But I know there's a page at UCF somewhere on SPI and that you're allowed to give extra credit if the majority of the class completes it. Completes it. And it's not for giving me a good rating, it's just completing it. So put whatever you'd like. Okay, any questions? Anything that we've reviewed so far? How's the codegen project going? Good. Yeah. So today we're going to be going over project review, and I'll be giving some examples of passing more than 6 arguments between functions. So you can see how the stack pass parameters look. It's going to be a really long example, just warning, but it should be hopefully a little bit enlightening and very helpful for codegen 3, where you have to implement the parameter and stack passing arguments. So to start, we can go over the 2 homework assignments from last time. So this is homework 22. Number 1, our function local variables, auto and C, are located at compile time or runtime. So first, does anyone know the answer to this question? And can explain why. Yeah.
I think it's like runtime because at compile time you can't know how many times the function's going to be called, so it's going to be allocated at runtime whenever it goes to the function block.
Yes, exactly. So where are local variables stored? The stack, right? And what does each function call have associated with it?
Stack.
A stack frame. And local variables are part of the stack frame. So for each one of those function calls, which we don't know how many times a function is going to be called at compile time, not always, then each one of those function calls needs its own set of local variables, and so we have to create them at runtime. And how do we allocate space for these local variables? What did we see in the previous lecture? What assembly instruction did we use? Or what register did we change to allocate space for local variables? Yes, RSP. So we decrease the value of the stack pointer to allocate space for local variables. We're going to see more examples of that today as well. Does anyone know what the auto keyword is in C? Have any of you ever seen this before? Yeah.
Is it similar to the bar keyword in other languages?
Kind of. It's actually, this is allowed in C programs. It's a storage class specifier. This is valid in C code. In fact, all of your variables have auto applied by default to them. It just means that there are located space for automatically on the stack at runtime. So when the function is done being called, they're automatically deallocated for you. But I think the auto goes here, it might go here. I'm not sure. I'll just try compiling this and see what happens. Yeah, it worked. So you can use auto pretty much anywhere in C, and it just means stack allocated, automatic storage. Yeah.
I would assume compiler optimizations can, like, I guess, count if a function goes all ways and optimize for that. Would auto kind of ensure, or is there, like, would there be a way to ensure that?
That's a good question. Are you saying like if a variable is used once, would it just inline the variable's value instead of allocating it on the stack?
I would assume it's like optimizations.
Optimizing compilers will do that. That's called constant folding, constant propagation. I don't know if the auto keyword will prevent that sort of optimization from happening.
But is there maybe a way to ensure it does? Is there a reason to do so?
I don't know. Good question. Yeah. Yeah.
Because of the existence of auto, does that mean you can manually allocate stuff to the stack in such a way that
To the stack, I'm not sure, but we can always manually allocate space on the heap using malloc. So I think you can also, use the register keyword and locate a variable in a register specifically as well. So some lesser known C, trivia. But yeah, now you should know by this point what exactly that keyword does. Yeah.
What happens if you try to put like everything in a register where it doesn't have enough like space?
You might get an error. I don't know. You might want to try that and let me know. But you probably would get some sort of compiler error if you did that. Also, I've noticed this before as well. You can't take the address of register variables because they don't have an address or in a register. But I don't know. These are all like random things, not really related to the course. So I won't belabor them. Okay, so number 2. If some function definition has a local variable x, will that variable always be assigned a single memory location in any possible program that has such a function? Nope. You have an answer?
No, it wouldn't.
Yeah.
It would be in a with response stack.
Yeah, so it wouldn't be. So every time we run our program, it will be given a different virtual address. Some things we'll talk about later in the stack smashing lecture is that memory is virtualized and it's also randomized. So the address of functions on the stack is going to be random every time you execute your code. So we don't know where variables lie in memory. And to verify this, what I could actually do here is just print the address of x in this program. Oops, gotta include standard io.h. You can see I'm not even recompiling the program, but the address is changing. The printed address is changing each time. So that just demonstrates that the address will always be different. Yeah?
can't the address also change in the middle of runtime? Because like doesn't the system try to optimize memory space by shifting stuff around?
The address of a variable will not change at runtime. Not that I'm aware of. No. You can change the address at which some allocated memory begins. That can be changed, but that has to be done manually, not automatically. Okay, so number 3. The following are the contents of a stack frame. Label which ones are caller created and which ones are callee created according to the x86-64 System 5 ABI. So first, the callee saved registers. This is like the easy one. It's it's in the title. The callee, yeah. The stack parameters. Caller. Why does it have to be the caller?
Because the caller puts the parameters on the stack, and then the callee will retrieve them.
Yeah, so the caller is the one making the call. The caller has access to the arguments. The callee doesn't know what the caller is passing to it. So the caller intuitively has to be the one to pass the parameters to the callee. The return address,
Caller.
the caller. So the caller issues the call instruction, which will push the return address onto the stack. The local variables,
Call
yeah, the callee, so it's within the scope of the function being called. The register parameters,
caller.
yeah, it's also the caller, so I don't know if you all have implemented that part of your compilers yet, but the caller is also going to be the one responsible for setting up the register parameters. How many parameters are passed via registers?
6.
6, right? The first 6, and the rest are pushed onto the stack. And then the old base pointer is pushed by what?
Calling.
The callee, yeah. Yeah.
Regarding the registers, what does the system do to determine what goes into the register and what gets put into the stack? So I assume the register is gonna be much faster than.
Yeah, so the ABI tells you some of this. Yeah. So it'll tell you how to pass which arguments to functions need to be passed via registers. The first 6 arguments to a function will be passed via registers. And in terms of local variables, that might be up to the compiler to optimize, but according to the ABI, they should be pushed onto the stack.
So is it just like in order, like it doesn't matter?
Yeah, yeah. For arguments to functions, it's the first 6 in order that are pushed onto the stack.
Alright.
Or, I'm sorry, put into registers. The rest are pushed onto the stack. Yeah. Yeah.
You get any difference between the return address and old base pointer? So the caller gives the return address, which is the line after that call function, right?
Yep.
And then what is the old base pointer point to?
The old base pointer is the base of the caller's stack frame.
Ah.
Yeah. So we have a difference between addresses in memory and addresses for instructions. And the return address is going to be an instruction address. The old base pointer is going to be a memory address for the caller's base pointer of its stack frame. What register in the ABI is meant to hold a pointer to the currently executing function's stack frame? RBP, right? What is the greatest number of active stack frames that will exist in memory at one time for the factorial function in the following program?
N plus 1.
N plus 1?
5 plus 1.
Yeah. 5 plus 1. So let's take a look here at the trace. So I'll put this on the left. I'll put this Excalibur on the right, and I'll put this on the left here. Oops. Okay, if I can get this to cooperate. There we go. Okay. So we have factorial. Make this a different color, and also bigger. Factorial of 5 is going to be the first call. The factorial function here checks if n is less than 2, and if it is, then it returns 1. Otherwise, it returns n times factorial of n minus 1. So we have factorial of 5. That's not going to trigger the base case for this recursive function, so we're going to go down to this else condition and call factorial of 4. That's going to trigger factorial of 3, factorial of 2, and then factorial of 1. And then in factorial of 1, we're going to return 1 because 1 is less than 2. So actually, I've counted 5 frames here. Not sure if there should be... Oh, yeah, you're right. Oh, ask for the factorial function, though, in the question.
Okay.
But if you're counting main stack frame, then yeah, there would
I
be
thought it
an
was like
additional...
the whole thing, the whole piece of code.
Yeah, no worries. That's extra details. But so your classmate's saying if you were to count the stack frame for the main function as well, which is called once, then we would wrap all of this under one more call to main like this. And that would be a total of 6 different stack frames active at once. But if we're just looking at factorial, it's just going to be these 5. Yeah.
For the previous question, why was it not RSP, but it was RBP?
Oh, so what does RSP point to? The top of the stack. Whereas this previous question asked a pointer to the currently executing function's stack frame. So the base of the currently executing function's stack frame, where all its local variables and passed-in parameters are relative to.
I think that frame part's not tripping that work. Is that like the whole picture you were showing last lecture?
I'm going to show more of it again this lecture, but yes, it's the illustration of the stack, and each function call has its own value of the RBP register. Okay, I think that's it for this homework. Any questions before going on to the next one? Okay, so the next homework 23, answering your question, hopefully. Draw the stack frames for the following two functions. After running main and calling f before f returns, remember to include the return address, the old base pointer, and the local variables. Okay, so the two functions here, we have main and f. And it's not asking us to translate this to assembly, just to show the stack frame. So I'm only going to walk through down here. I have the two functions shown. I'm going to walk through the execution of this code, the actual SimpleIR code, and also show how it modifies the stack. And I'm going to have two different colored instruction pointers here. The red one for main, green for f. Maybe I should just keep one to keep track of what function is currently running. I'll do that. Make this blue. And so we're going to start from main. We're going to assume main was called by some other function. In practice, what other function would this be in your compiled binary that's calling main? Underscore start. Yeah, that's the start symbol, the true entry point of your files that have been compiled on a Linux system. So we're calling main. We're assuming that the RSP, the stack pointer, is going to be at 128 to begin with. We'll just assume that's the address of the return address where it's stored. We'll set up the local variables. So first thing we have to do when entering a function, we have to actually push the old value of RBP onto the stack. So we'll push that onto the stack here. We'll assume that it's just 192, just I gave it an arbitrary value. And because we did a push, the value of RSP is going to be incremented. So we don't have all the assembly code here on the left. But after incrementing the value of RSP, what do we have to do? After pushing the old value of RBP, what do we have to do?
Add the new value of RBP to the stack.
So we just pushed the old RBP to the stack. What do we?
The new value.
Yes, set the new base pointer, the new stack frame base pointer, to the new value of RSP after the push. So this is going to become 120. That's where RSP currently is, 120. So we're going to set RBP to 120. And we can skip RBX, but what do we normally have to do with RBX?
Push it to stack.
We also have to push it to the stack. The ABI tells us that we have to preserve the value of RBX across function calls, but we can skip it for now. We're just going over this example here. We don't have all the assembly code on the left, so I'll skip over preserving that. What we'll do instead is we have to allocate space for local variables. So how much space do we decrease the stack pointer by? So 8 per local variable, but there's two local variables here, ret val and x. So we're going to decrement it by 8 times 2, 16. So 1, 2. And we're going to have it such that, if I can draw this here, this would be the address of ret val. So the ret val variable will be stored and will span these bytes from 112 to 104. And then the x local variable will span the bytes from 104 to 96. So let me see what the question actually had asked. After running main and calling f before f returns. Okay, so we'll stop before f returns. So I think that's all we need to do to set up the local variables. Any questions? Yeah.
What's the
The what?
What's the 192?
Oh, that was just the old value of the base pointer. I just had to have it be some value. Yeah, I didn't want to write old RBP because we're going to push it again to the stack later, so I wanted to make sure there's a difference between the two. But yeah, that's just some arbitrary value that I just selected for it to be. Yeah. Okay, so now we're assigning x to 2. So I'm not going to go through all the actual assembly instructions that would achieve this, but we're just going to put 2 to the memory address where x is. Then we'll say retval equals a call to f. So I'll leave this right here in red. And so what do we do with a call instruction? What's the first thing we do?
Push the return address.
We push the return address. So we're going to increment the RSP and place a new return address onto the stack. So we'll say from f. And now we're going to continue executing from within the function f. So now we have to do what? We just started executing a new function. What do we have to do first?
Create space for the local.
That's second. Close. First we have to, I think your classmate had said it. Yes, push the old value of RBP. So RBP now is 120. So we're going to push, so we're going to decrement the stack pointer to push onto the stack. We're going to place 120, oops, I'll put this right here. The old value of RBP before the call to F, we're going to put onto the stack right here. Now we can allocate space for the local variable x, which I'll change the name here to make it a little less confusing. I'll change it to a, that way it's clear that we're talking about a different x and not the same x in main. So how do we allocate space for this variable?
Offset by 8.
Yes, decrease the stack pointer by 8 again. So now we're going to store a here. And we'll skip the parameters setup and we'll go straight to a equals 3. And here, what we're going to do, actually, so I did skip a step, but what we should have done when we execute, actually this is fine. There were no parameters to, we didn't call f with any arguments actually. It seems to be a typo in the assignment description. Did anyone notice this?
Yeah, there's also,
Yeah.
at the end of the third function, was it, that it says, oh no, second function, it says that x in assigned to, the function f.
Oh, but it's in main. Yeah. I'll fix this. I'll fix this. For now, let's just assume that this call to f is followed by x, so that there was actually an argument passed to f, because f expects an argument. It has local variables and a parameter, a single one. So we'll assume that x is passed to f. If that's the case, because f has one argument, we need to pass it via registers, and we use the RDI register first. So we would store the value in x, which is 2. We would store it in the RDI register. And here, inside of the call to f, a would have the value 2 initially because it would extract it from that register as it was passed from the caller at this line here. I'll correct the homework assignment description with all this, but as long as you do the assignment, you'll get full credit. So here we're going to change the value of a to 3, and then we'll return a. So here, how do we return a value?
Move it to RAX.
RAX, so we would move it into RAX. That's how we return a value according to the ABI. So move the value 3 into RAX. And here, we can stop because the homework assignment told us to stop or give the state of the stack after running main and calling f, but before f returns. So maybe we don't have to change the value of RAX, but we're going to stop here right before f returns. Should I continue and show the full trace? Yeah, okay. So we've set RAX to 3. Now we have to return. So when we go to return, the first thing we have to do is deallocate space for the locals. So we'll increment the stack pointer by 8. Then we're going to restore the old value of the base pointer, which I actually had forgotten to update. The base pointer should have been set to what? I think it should have been set to 88, actually. That's where the old base pointer was here, so. But we have to restore it now, so we're going to set it back to 120. We have to restore the old base pointer back to 120. We're going to pop the return address now, rather than the return instruction. So we're going to go back to increment the stack pointer by 8, and we're going to branch back to right here, the instruction immediately following the call to F. And then we can just return X. So to return X, we have to deallocate space for the locals. So we'll deallocate 1, 2. And finally, deallocate space for the, or pop the old value of the RBP. So we'll set this back to 192. And then then we can execute, we can get the return address and go back to whatever function had called main. So that'd be underscore start. Okay, any questions? It's a little tricky because we don't have the assembly code, we have the SimpleIR code.
Is it bad if I kept pushing RBX onto the stack?
You should. That's good. I mean, I elided that here because it's not strictly necessary for this example. But in practice, you'd want to push RBX onto the stack after RBP. Yeah, to follow the ABI. And we'll see an example of that in the next example. Yeah.
So the original base pointer, when you have it, contains 192. That's RPP. And when you go down to the function, it calls the old base pointer again, but it gets the index of RPP instead of the value inside of 120.
So when you call a function, the current value of RBP is pushed onto the stack. So we're assuming here that 192 was pushed onto the stack, and that we're currently at 128. If we were to call another function, so if we were to first to call main, we would have to set RBP. We have to save the old stack pointer, so base pointer 192. Set RBP to the new address, which would be 120, and then continue executing from there. And then when all this is done, when all this code is done executing, we would actually pop this old value off the stack. So we're getting this off the stack and storing 192 back in RBP, and then incrementing the stack pointer by 8 because we popped it off the stack.
Oh, so RPP is just like a stack just calling itself, just like
It's,
just indexes, like a chain of like the linked list of indexes.
you can kind of think of it like that. It's like kind of like a linked list where we're going back and back and back to all the callers. We're tracing backwards at the call stack. Yeah, we're able to implement this with careful instructions in our compiled code, careful ordering of instructions. Okay, so let's see, let me put this over here. Question 2, write move instructions, implement x equals 2 above in function f. We'll just say x equals 2. I'll just open this up in Vim and type this in real quick. So how do we do x equals 2? We should hopefully be familiar with this by now. What are the move instructions we'll need to use? Assuming, so okay, let's look at back the diagram here. X is the second argument, so what should x's offset be? 16. If we were pushing RBX as well, it would be negative 24. Or, yeah, it would be negative 24. But we'll assume negative 16. So, okay. So how do we assign the value of 2 into x?
Move and the dollar sign for 2, and then negative 16 in parentheses R.
Yeah, exactly. Yep. So with our compiler, for the more general solution, what we do is we move these values into temporary registers first, so RAX would go first. And then you would move that into negative 16 RBP. The reason for this, the reason why we have you do this in your compiler is because it's more general and it allows you to implement assignment from variables the same way as assignment from integers, because you cannot have two memory indirection operands in the same assembly instruction. So we couldn't have something like negative 8% RBP in one move instruction. So to avoid that issue, we have you follow a template where you move into a temporary register first and then move into the destination variable. Yeah.
So we can't have like two offsets at the same time?
No, yeah. It's just not one of the modes according to the ABI, or the instruction set, I should say. Yeah. Now, I think different architectures besides x86 might allow you to do this, but with the instruction set that we're going with, you're not allowed to do this. Yeah. Okay, and then how are parameters passed according to the ABI? We had said this earlier. First 6 by register, anything after that by the stack. What's the detail or the twist with pushing them onto the stack? Have you implemented that part of your compilers yet? Okay, and you're probably not familiar with it, but there's a horrible detail that you have to follow that's really confusing. They're pushed onto the stack in reverse order, all the arguments after the 6th. It's not that bad, it's just a little annoying. But yeah, the arguments are pushed onto the stack, 7, 8, and so on are pushed onto the stack in reverse order. So we'll see an example of this shortly. Okay, any questions? All right, so I think we can take attendance now. Let's refresh the page. I'll pause the recording here. Okay, so yeah, I see you grimacing. So what I want to go over now, before we, well actually I guess there's two things we can do here. Either one, we can talk about the project, if anyone has any questions they'd like answered, any burning questions about the implementation or the codegen project itself, we can go over that. Otherwise, I have an example I prepared this weekend, and I stepped through it so I made sure it's correct, of passing 8 arguments to a function. So we can see how all of that looks at the stack level and the assembly level. Not sure if anyone has any questions, we'll go over those first, but otherwise I can just go over this example. Okay, so I guess the long example it is then. So in this function we have these code snippets here. We have 2 functions, main and f. Main has 2 local variables, x and y, and it's assigning x to the result of a call to f, passing 1, 2, 3, 4, 5, 6, 7, and 8 numbers to it. And then it's returning 0. And then f, meanwhile, has 8 local variables, a through h. Also, they are parameters, and then it just returns h, and that's it. So, like, minimal example of passing 8 arguments to a function. And brace yourself. I have a very long code snippet here. I tried to fit it all in one slide, and I think it all fits. Hopefully it's legible. Okay, yeah, barely all fits, but I think that's good. I don't know if this is ridiculous, but I think it's worth stepping through so we can see how all this actually, I'm going to go through all of this, you can see how it works at the detail level.
Did you resume the recording?
Did I what?
Resume the recording.
I did resume the recording, so yes, you will have access to this later. And I saved all these notes so I can do it again next semester.
It's better to double check.
Okay, so any questions? We have the assembly code for main, the assembly code for F, all the different registers down here that we're going to be using. and the stack is over here on the right. We're going to assume that the return address for main, I'll make this in blue, the return address for main was pushed on already by probably underscore start, and the address, the stack pointer currently is pointing at 232.
And that's the return address from main back to underscore?
Back to underscore start, yep. And we're going to assume that the old base pointer just has this arbitrary value, 264, assigned to it. I know it's kind of cluttered, but I needed to find space for all this somehow, so maybe I can drag this all a little bit up. That's a little bit better, I think. All right, so I guess we can begin. Yeah, question?
Yeah, just making sure I'm with you. Beginning on the right side with 240 that's just dictated by counting down by 16, or, well, no, not that, but, by 24, from what you said is the arbitrary starting point here?
240. No, I just chose an arbitrary starting point for the stack.
Oh, okay.
Yeah. We're just choosing an arbitrary value of RBP, and I just wanted to choose an arbitrary starting point for the stack, for the visualization of the stack. The stack goes up higher than this.
Okay.
There's
no relationship between those things?
No. We could put, like, maybe what I should do is put 3 dots here, and this could be like 0x ff. I don't know exactly what the highest address would be, but just to show you that it's really, this is just like a shorthand for going to the rest of the stack. Yeah, we don't know what's after this. I'll just leave it as 240 so we can be super concrete. Yeah. But this is just a slice of the stack. Okay, so we can begin. So we have the label main is where we start. The first thing we'll do is push the value of RBP onto the stack using the push Q instruction for push quad. So it's a quad word, 64 bits, I should say. We're pushing the value of RBP onto the stack. So the first thing we do when we push is increment the stack pointer, or decrement it, I should say, go down by 8. Then we put the old value of RBP onto that location that the stack pointer is currently at. So the stack pointer is going to be at 224. So we're going to put, 264 onto the stack at this address. Now we're going to save the old value, or the new value of RSP, into the base pointer. So we're going to overwrite the base pointer with the new value of RSP.
So sorry.
All good. So we're going to change RBP to what? What's the current value of RSP? 224. Now we're going to push, because the ABI tells us to, we're going to push the old value of RBX onto here. So the first thing we do with the push is decrement the stack pointer. Then we're going to put RBX onto here, so we're going to put the value of RBX into the stack. It's 42, again, just an arbitrary value, no relevance to anything. And now we're going to do what? After we pushed the old base pointer onto the stack and the old RBX value, what do we have to do after that? Allocate space for the local variables. And we do that by subtracting by some number. So we subtract by 8 times the number of local variables. Main has 2 local variables, x and y. So we're going to subtract by 8 times 2, 16. So we're on this instruction right here, subtracting 16 from RSP. So 1, 2, that should be enough space. What we've effectively just done is locate space for x and y. And now we're going to actually execute the function call here. So now we're ready to actually execute some code. So we're going to execute the function call here. So we're doing this line of code here, x equals call f 1, 2, 3, 4, 5, 6, 7, 8. The first six arguments are going to be stored into registers. So we're going to move the value 1 into RDI. 2 into RSI. 3 into RDX. 4 into RCX. And 5 into R8. And 6 into R9. One thing I'll point out is that if you want to try and remember these registers, you don't have to for the exam, but one kind of mnemonic that I found helpful is that these two both end in I, so RDI, RSI. These both end in X, RDX, RCX, and these two end in a number, so R8, R9. It's not a perfect mnemonic, but it's a little bit of a tool to help you remember them if you want to. Okay. Now, the remaining arguments have to be pushed onto the stack in reverse order. So we're going to push 8 first, because 8 is the last argument. We're pushing them onto the stack in reverse order, starting with 8, then going to 7. So RSP is right here. We're going to decrement it by 8, and then push the value 8 onto the stack. Oops, should be red. Then we're going to execute the next instruction. So we're going to push 7 onto the stack. So we decrement RSP by 8. And then, oops, there we go. Push 7 onto the stack. Now we execute the call to F. So what do we have to do for the call to F? Push the return address onto the stack. So we're going to decrement this by 8 and put the new return address going from F back to main onto the stack here. So now we're at F. So we'll execute some setup function. So this is part of what? The function prolog. And here we're saving the old value RBP. So we'll push RBP onto the stack. Go down here. What value are we storing? 224. So now we're taking that value we had earlier. I can just drag it from here. Putting it onto the stack. And now what are we going to store in RBP? RSP, so what should RBP be set to now? 168. Then we push the old value of RBX onto the stack, so we're going to decrement the stack pointer by 8. And we didn't change RBX. Can be a more complete example would change RBX, but we didn't change it, so I'm just going to set it to 42 again. Push that onto the stack again. Now we have 8 local variables, A through H. 1, 2, 3, 4, 5, 6, 7, 8. We need 8 bytes, I should say, of space for each of them. So 8 times 8 is 64. So we're going to subtract 64 from the stack pointer to allocate space for those 8 variables. So I'm just going to count by bytes here, by 8-byte width. 1, 2, 3, 4, 5, 6, 7, 8. 64. So we were at 160 minus 64. I think that's 96. This seems to be correct. What we've effectively done is a located space for A, B, C, D, E, F. I think I made a mistake here. Actually, wait. No, I didn't. No, I didn't. Yeah, H. For a second, I thought that I left out G, but thankfully I hadn't. Okay. So it seems to be correct because after adding those variables in order, the stack pointer seems to be pointing to the begin point, the beginning point of the correct last local variable. So we can consider this as done, move on to the next instruction. Now for these next set of instructions, all these move instructions here, we're going to be getting the values out of the parameters and putting them into local variables. So I'm not sure if you've implemented that functionality yet in your compilers, but that's one thing codegen 3 asks you to do, is implement both the passing of arguments here and the extraction of those arguments into local variables. And again, this is just something we do for the you don't have to necessarily do this. We just moved all the parameters into local variables as well to make the compiler easier to reason about. So the first thing you have to do is extract the value of the first parameter, which is going to be stored in the RDI register. So we're going to do the value in RDI into -16 from the base pointer. So RDI has the value 1. The base pointer is at 168. 168 minus 16 is going to be what? 168 minus 16? So 16, yep. So right here. 1, 2, 152. That's going to be A, that should be correct because this is the first parameter we're extracting here. So these following ones are all going to be subsequent values of 8, multiples of 8, negative. So I'm just going to be putting these in here one at a time. I'll go through them quickly. So this will be 2, this will be 3, 4, 5, 6, 2, 3, 4, 5, 6, yep. And we'll stop there, and now we're going on to this instruction here. So that's the first 6 register parameters. The remaining parameters are going to be on the stack. So we need to do something different to get those parameters out of the stack and into our local variables. So because stack parameters are pushed onto the stack before we issue the call instruction, they're going to be at positive offsets from the base pointer, not negative offsets. So to get the value in the final parameter, because remember they were pushed in reverse order, we're going to say -16 RBP. Actually, I guess this is the 7th parameter. So RBP is 168. 168 minus 16 would be, starting here, 1, 2, that's 16. So plus 16, I should say. 168 plus 16 would be 184. 184, that's going to be 7. So we move the value there into RAX. So we'll say 7. Then we move the value out of RAX into -64 RBP. RBP is at address is 168. So 168 minus 64 should be 104. So we'll go all the way down here. At 104 we have the 7th parameter G, so it seems like everything is lining up. So we're going to put 7 right here. All right, any questions with how we did that first? We extracted the value of that first stack parameter. Okay, so we'll do it again. So now we're going to go at 1 positive offset greater, 8 greater the positive offset. So we're going to go at 168 plus 24. That's 1, 2, 3. And then 192, that's going to be 8. So we're going to get the value 8. We're going to put it in RAX. and then we're going to move the value in RAX into negative 72 RBP. So RBP is 168 minus 72. That should be 96. So 96, we're going to put the value 8 right there. Can anyone tell me, I'm going to zoom in here for a second, why we don't just combine these two instructions into one? Why do we have to move into an intermediate register first?
You can't move one pointer to, sorry, that's not the right word. You can't move one location on the stack to another location on the stack.
Yes, we can't have any memory indirection. We can't have two memory indirection operands in the same for the same instruction. There's no mode for these instructions that allows for that. So we have to go into a temporary register first, and then move that into negative 72 RBP, the destination location. So we've done that. Now we have to move the value. So we're setting the return address here. So here we returned H. So H is at negative 72 RBP. So we're going to move the value in H into RAX. It's already stored in RAX, so I'm not going to update the diagram at all, but it's already there. So we've set the return address. Now we have to deallocate the space for our local variables. So RSP is at 96. We're going to add 8. So 96 plus, or 64 I should say, 8 variables worth of space. So 96 plus 64, I think that's 160, correct? I know it has to end in 0 because 4 plus 6 is 0, so I think that's correct. Yeah. 160. So we've added this. We've deallocated space for all those locals. Then we're going to pop the value of RBX, restore that. So we're going to say 42, put that back in the RBX register. It's already 42, so we're not going to change anything. But we decrement, after popping, we have to decrement the value of RSP by 8, or increment it, I should say. Then we're going to restore the old value of RBP. So we're going to take the value here, 224, store it in RBP, and then we're going to increment the stack pointer by 8 again because we just popped. And now we're going to issue the ret instruction here. So what will this do? What will the ret instruction do? Yeah, so we'll get the return address. So we're going to continue executing here. But how does it get the return address? What does it do to the stack? I appreciate the sound effect. Yes, it pops it from the stack. So don't forget that. Yeah, we're going to increment it by 8 again after getting their return address. Cool. So now we're back to main. One thing you have to do after setting up those stack parameters, we had to actually change the stack when we pushed these stack parameters onto it. So now we have to undo those changes to the stack in order to call F. So to do that, we're going to do the same trick we do to deallocate local variables, and we're going to add to the stack pointer. So we're going to add 2. So 1, 2. 2 variables worth of space, so add 16. Let me put this here, and yeah.
Do X and Y still exist? The shells? Oh.
Yep, they're still there.
Oh, wait, so, the next step is. Oh, okay.
Yeah, we deallocated, so that's important. We deallocated the parameters. We didn't deallocate the local variables. We deallocated the parameters that we have pushed onto the stack in order to make the call to F. So when you have more than 6 parameters, not only do you need to push the arguments onto the stack in reverse order, you have to remember to deallocate their space afterwards. Otherwise, your stack pointer is going to be pointing at an incorrect address. Always make sure to undo your changes after you're done. Yeah. we have to do that manually. That's what this add instruction here is doing. This is the one that's undoing the allocation for the parameters, for the stack parameters. Yeah. Good question. Okay, now we're moving RAX into negative 16 RPP. What does this correspond to? This seems kind of random. Why are we suddenly accessing RAX?
You're getting the return value from the function?
Yes, exactly. We're getting the return value. So remember, here, we had set x equal to the result of the call. And the ABI specifies that the return address is always, the return value will always be in the RAX register. So after a function is called, in order to get the return value, we have to manually move it out of the A register, RAX. So
what's the return value in this scenario?
What is the return value?
Yeah.
So in the function up here, we return the value of h,
Ah,
which we had correctly set on this line inside f. So it should be equal to 8, and that is the value of h. So it seems like things are going according to plan here. So we'll move 8 into negative 16 RBP. RBP is going to be at 224 now because we restored it, so it's back to 224. So 224 minus 16 is going to be 208. That's going to be x. So we're going to put the value 8 inside x. And now this is setting the return address for main. Remember, main returned 0. So here we're setting main's return value, not address, value, to 0. So we're going to overwrite RAX to be 0. And now we're done with main, so we have to deallocate the space for the locals. So we're going to subtract 16. So 1, 2, 2 variables worth of space. Now we have to restore RBX, so we're going to pop the value of RBX. It's 42 here. We're going to store this result in RBX. RBX is already 42, so I don't have to change anything. So I'll leave it as it is. But after the pop, we have to increment the stack pointer by 8. And now we'll pop the value of RBP. We're going to store pop whatever values here and put it in RBP. So we're going to get the value 264, which is that arbitrary value I mentioned at the beginning of this example. So then we're going to put that back in RBP and then put the RSP back up by 8 more again. And now it seems like everything's right because our RSP is correctly pointing to the return address for main, where it was when we began this example. So finally, we'll execute the ret instruction. The flow control will go back to whatever function had called main, and the RSP will be incremented by 8 one last time. Okay, so any questions? Yeah.
Is that last move on the f function useless?
This one?
On the f function?
This one? Or this
Yeah.
one, right?
Yeah.
So what is this move doing?
Isn't that's putting 8 into Rx, right?
It is.
But isn't Rx already 8? Because it was 8 to move into.
Oh, sure. So effectively it's useless.
Oh, okay.
But we still have to do it according to, if we're making a compiler proper. Maybe an optimized compiler could do away with that. You're correct. But what role does this serve? Why do we have this move instruction? What does it correspond to?
Yeah.
Return value?
Yes, we're setting the return value. That's why. So here we're returning h. So in order to do that, to compile that line of code sort of directly, we're moving the value from negative 72 RBP into Rx.
So when do you have to do the queue? I know you said for quad, but I'm not sure when.
Oh, that's just a specific, I think you might be able to actually use push, but I use push Q because it's specific for quad words, which are 64-bit values. So a word, minimum addressable unit on x86 64 CPUs is 16 bits, 2 bytes. 2 bytes. A quad word would be 4 of those. So 2 times 4, 8 bytes, 64 bits. So a lot of these assembly instructions, you'll have like Q put onto the end for quad, because it's 64-bit values. What?
But you said it's not necessary?
I'm not sure if it's necessary or not. I can't remember if, I mean, we could check. Yeah, push is probably fine. According to this specification here, which we've been using throughout the course I've been referring to, push will probably be able to tell. I think push can just tell based off the type of the operand whether it's 64 bits or not. Yeah.
Do we have notice example inside and out? Are we like,
Yeah, you're pretty good. If you know this example inside and out and can explain why every line of code is written the way it is, why we have some seemingly useless lines apparently, like, well, you can see like that they're ineffective, why they're there, then you'll definitely get an A in the final, I would say. And just be prepared that the long response question might ask you to not necessarily draw a stack, but to translate something to assembly code, translate some IR to assembly code. I'm not going to ask you anything exceptionally difficult or complex, nothing like this. The idea is, practice more than you actually need to perform for the test. So.
I feel like drawing a stack would be easier than translating from IR.
no,
Really?
If you can, I would recommend, please know like the basics of the function prologue, function epilogue, how to translate the different kinds of instructions from IR to assembly. Know how to do that, and then if you can understand how the stack is operating as well, you're golden. Okay, so any questions? Yeah.
When you were in the F function, after allocating the space for the 8 variables, why did you start with like -16, like to put like 1 in A and then 2 in B?
This is here.
No, like after sub the 64.
After sub 64, right here.
Yeah, why did you start with -16?
So let's go back to this line. -16. This is from -16 from what RBP was at that time. I think this was 160. That's what RBP was when we executed this line here. So 160 minus this is going to be 144. That's going to be A. So RDI is going to store the first parameter that was passed. So this value 1 is going into RDI, or maybe I'll draw it this way. The value 1 goes into RDI, and then that goes into A as the first parameter.
Okay, and you just use it like the -16 to offset into the A variable?
Yes, -16 is just the offset into the A local variable here. Yeah. Normally I like to draw the offsets if we had 2 functions here, so I would have to draw 2 sets of offsets, and that'd be even more stuff than this already cluttered slide. So. Yeah.
So, just the acts of like popping, like moving RSP up is deallocating variables.
Yes, effectively, yeah.
Okay.
So the values are still here in memory, but we haven't zeroed them out or anything. But they're no longer accessible to us. And maybe we could, but we're not supposed to be able to access them.
And the goal is always to be at the return address whenever you use return.
Yeah. When you get to the return address, you should be pointing, the RSP should be pointing to a valid return address. Otherwise, bad things can happen, and attackers can manipulate this intentionally to perform what's called stack smashing, where you change the return address to some arbitrary other function.
Was that what your research
No, my research is all on stack smashing. Yeah. There's been a lot of research on that in the past, and we'll talk about some of the mitigation techniques that have been employed to prevent stack smashing. There's a lot of them. For example, there are address space layout randomization, which we'll talk about, where your virtual addresses are always randomized, as we saw at the beginning of this lecture. Whenever I ran that C program that I wrote, the address was always changing. There's also something called canary values, where you set special values around the return address of functions, and then if a bad actor in their malicious code somehow modifies those canary values, then some mechanism in the operating system is alerted and the process is terminated.
So it's like pushing extra stuff on the side.
Yeah, you're like padding the return address with extra values that have to be kept safe. Yeah. I don't know if you all heard of a canary in a coal mine, like that saying. That's what it comes from. So we'll talk about that more in the next lecture. Yeah.
The final exam is like cumulative, or is it just like the whole pointers?
It's cumulative. We do have a final exam review day where I'll go over this in more detail, but I've already prepared the final. I printed it. It's on web courses. Here are the big details, the question breakdown. So it's going to be 26 multiple choice questions, 3 short answer questions, and 1 long answer questions. This time around, the long answer is going to only be worth 4 points, not 5 like it was for the midterm, but each short answer is going to be worth 2 points, not just 1. And for the multiple choice breakdown, 10 are going to be from the midterm, 16 are going to be from the second half. And they're going to be easier questions from the first half as well, I will say. I'm not trying to trick you or make you memorize random minutia from the first half of the course. Yeah?
When you say esoteric, do you mean like they're the exact same questions or just same source material?
They'll be, I believe they're actually, no, they're different questions. They're different questions, yeah. They're new questions that I made, but they're from the same source material. Yeah. Yeah.
The change in point values from on the short answer, is that just a quirk of the final, or is it is it a new iteration?
Just a quirk of the final. The point is to get them to add up to 36 points.
Sure.
That way you can divide your score by 3 and get the total number of percentage points that it contributes towards your score. I just like keeping the numbers to be round numbers. So with 36 total points divided by 3, that gives you 12. If you get 100%, and the final is worth 12 points towards your final grade. And for the short response questions, those may or may not include first half material as well, but I don't give you the breakdown on that. And I can't remember if I had put any any stuff from the midterm on this semester or not. Okay, so I'll save this diagram now before I forget. Canvas too big. Okay, cool. And, does anyone want to review the project at all? Any of the code, any questions about the implementation? We have 30 more minutes if you want to go over, if you have any questions about that. Okay, I will bring up one thing that might be important. Just a random thing that one student had an issue with last semester that I figure I'll mention now and maybe save you some heartache. Be aware that C and C++ will implicitly coerce types into other types. So if you are trying to compare a size t type to an int type, there'll be some type changing that goes on here, which could lead you to have infinite loops. Just be very careful when comparing integers of different types. I don't want to give you too much, but just make sure that if you have, like, for instance, a for loop with an integer I, and you're comparing it to some variable, I don't know, n, just make sure that n is also an integer. And if n is actually a size t, maybe make I a size t to match. Just something to be careful of. And especially if you're counting down to 0, be aware that size t is an unsigned type, so there is no 0, nothing less than 0. So if you end up going less than 0 with a size t type, you'll wrap back around to a really large number. So you might end up in an infinite loop. So just make sure not to check for things like, don't check for that. That's going to give you an infinite loop. In fact, maybe I'll demonstrate it. Set it to 1. Oh, well, that actually finished. Oh, I is, yeah, I is greater than 0. Oh, greater than or equal to is what it should be. Yeah, now it's hanging. So, while it spins, what's going to happen is I will be equal to 1, and then I will be equal to 0, and then because there's no such thing as a negative value for a size t type, I wraps around to something like int max, or something like that. I don't know if it's int max exactly. It's whatever is the maximum for a size t type. So you end up in an infinite loop, and then I becomes int max minus 1, and then dot 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 I equals, and then it's back to the beginning. So just be careful if you're, because I will say when you're pushing those arguments onto the stack in reverse order for the parameters, if you're looping down like this, just be careful that that you have your signedness correct. You're not trying to compare an unsigned value to a value less than 0. Yeah?
In C, can't you do conversions? Like, can't you, like, convert it to, like, some sort of format for that?
Yeah, you can do typecasts. You can do a typecast. So you could say, like, int, but that's not going to solve this problem in this case. Because this happens after I has already been, I don't think this will solve the problem. After I has already been, well, maybe it will, I'm not sure. But it's kind of messy. The better thing to do here would just be to convert I to an int type. That's a simpler solution.
Would it still work if you previously declared I outside the loop and then did the conversion within the loop, like doing parentheses and then I equals 1?
Let's try it.
No, I mean on the when it gets added.
Well, this already worked, it seems like. Yeah. And we get no warning either, so. I don't know. Yeah, just keep that in mind. Sidedness of the variables you're working with, so you don't get an infinite loop. All right, well, if there's no more questions, then you guys can leave early. And next lecture, we'll be going over stack smashing, which is, again, is a bonus lecture, but attendance is still required, but the content will not be on the exam.